Welcome to everybody present here. And I'm glad that you could join this lecture, or rather these lectures, which promise to be illuminating and revealing. So before we start, I would request Professor S.K. Tripathi, chairperson of this department, to address. Thank you.
So, good afternoon to all of you. It gives me an immense pleasure to welcome all of you. Professor Vipin Srivastava, University of Hyderabad. Professor Arvind, IISER Mohali. Professor Arun Kumar Grover, ex-Vice Chancellor of our university and motivating to all of us in the department. Professor P.K. Aluwalia, IAPT President. Many other guests present in the audience. All of you know this, our physics department is a very vast history. It starts from Lahore, then shifted to Chandigarh after traveling a lot of places, Hoshiarpur, Shimla and other places. I will not say too much about the university and the department. All of you are knowing. So this is the fourth lecture in the Nobel Prize in Physics 2024, which is organized by the SPSTI, Society for Promotion of Science and Technology in India, and especially this lecture in collaboration with the Department of Physics. So I welcome to all of you for this lecture. I will not take much time. And once again, good afternoon to all of you.
Thank you, Professor Tripathi, especially for extending the facility of this hall to us. Thank you. And now I request Professor Grover to come and give opening remarks. Especially, he will give a brief on the lecture series.
Good afternoon, all of you, my old colleagues, peers, teachers from the department, students, ladies and gentlemen. So we commenced holding lectures on all the Nobel Prizes, Turing Award, Nobel Prize, and the World Food Prize every year during the pandemic times. So in the year 2020, when everything was going online and when these prizes got announced that year, so Professor Pasi, who was then the Vice President of SPSTI, he said that we should hold these lectures in all these 8 prizes every year. So this process commenced 5 years ago. This is the 5th year in the running. So in the first 3 years, everything was online, but all those lectures are available on the SPSTI site. Last year, we did few lectures in the physical mode, few in the hybrid mode. But this year, our president, Mr. Dharamveer, said, no, we must do these lectures in the physical mode and add the hybrid mode to it. It should not be the other way around. So we have held only 3 lectures physically so far. This is because the prizes get announced in the month of October and they get awarded by 10th of December. So when it was online, we tried to hold all the lectures before December 10. But when you have to do it offline, then we need audience to listen to these lectures. And since the semester ends in November, so students are not available from 15th November onwards. So we have to revise our strategy. And from this year, we are going to do it at least whichever lectures we can hold it up to 15th of November. Physically, we do it. Rest of the lectures, we do it after the students come back in the second semester. So today is our 4th lecture. It's the beginning of the second semester, and 2 more are remaining. One a Nobel Prize in Peace, and the other is a Nobel Prize in Economics. And these 2 lectures will be given by Economics Nobel Prize will be given by Professor Arun Kumar, the eminent economist of India, who is an ex-professor from Jawaharlal Nehru University. And in the context of this year's Nobel Prize, he is going to describe to us how the Indian economy has progressed since the Indian independence. And this assumes additional significance in the backdrop of passing away of Dr. Manmohan Singh, who had played a significant role in giving a new direction to the economy in the early 90s. And it's that direction only which is continuing even today. So Arun Kumar tells us how we have economically, political economy has evolved since 1947. And Dr. Ravi Grover, who is a member of the Atomic Energy Commission and who was the negotiator of Indo-US nuclear deal, he is going to give a talk on Nobel Peace Prize. And in that backdrop, he is going to describe how India fares in this disarmament movement and this having nuclear energy for peaceful purposes. So, and this talk also assumes additional significance in the backdrop of the passing away of Dr. Manmohan Singh. So these 2 talks will be delivered physically at IISER Mohali on February 13 and February 14 respectively. The February 13 talk by Arun Kumar is at 3 p.m. and the February 14 talk by Ravi Grover is an evening talk at 5 p.m. So buses would be available from Punjab University to go to the IISER Mohali on both these days. So this is the background of this year's lectures, and I hope next year we'll put up a better show. After the Nobel Prizes, there are 3 still more lectures to come in this year. That is, which will get announced in the month of March. Abel Prize and Turing Prizes are announced in the month of March. And the World Food Prize also gets announced in the world of in May. So we'll hold these lectures before the end of the second semester, the remaining this thing. So total of 8 lectures or 9 lectures. And this is the responsibility that SPSTI has assumed in cooperation with all the institutions in the Chandigarh region, plus the Chandigarh chapters of INSA, NASI, and INYAS, that is Indian Young Academy of Sciences. So this is a collective activity. Lectures are distributed in different institutions depending upon the audience and the location available and the convenience of the speaker. So this is the 5th year in the running, and hopefully this will continue for as long as the university exists and as long as the Nobel Prizes get awarded. Thank you very much.
Thank you very much, Professor Grover, for telling us about past, present, and future of this lecture series. And now I request Professor Suman Bala Beri, another very eminent member of SPSTI and of this department, of course, who will introduce our guest of honor, Professor Arvind. Professor Suman Beri.
Good afternoon, everyone. It's my privilege and honor to introduce Professor Arvind, guest of honor today. Professor Arvind is a professor of physics and Dean R&D in Indian Institute of Science, Education and Research, that is IISER Mohali. Professor Arvind was the Vice Chancellor of Punjab University, Patiala from 2021 to 2024. He is a quantum physics scientist who worked to improve the university's academic, financial, and administrative conditions. Just a few, there are a long list, but just to mention a few. During his tenure as VC in the Punjab University, he increased the monthly grant from the state government from 9 crore to 30 crore rupees. He launched 6 new 5-year integrated courses in 21-22, reduced the university's debt and interest rate, and many more achievements in his side. So he did his master's in physics in 1990 from Indian Institute of Technology, Kanpur. He obtained his PhD from Department of Physics and the Center of Theoretical Studies at the Indian Institute of Science, Bangalore in 1997. Then he joined the physics department of Guru Nanak Dev University, Amritsar as a faculty member. During 2002 to 2004, he was in the physics department of Carnegie Mellon University, Pittsburgh, as a special faculty there. He joined as a faculty member in physics department of IIT Madras in 2005. And then he moved to IISER Mohali in August 2007. And at present also, he is in IISER Mohali. His research interests are, if I start, it would take much time. So I'll just mention very briefly his interest. The field is quantum information, quantum computation, foundations of quantum mechanics, quantum optics, physics education research. And he has been associated with the National Quantum Mission, which interested in the developing new teaching methods and experiments for physics teaching in the context. They are in the IISER, they are setting up a laboratory also for physics education. I know him personally. He's so dedicated for the new experiments, the new teaching methods. We have been, I think, held his lectures here also in the same auditorium. So not taking much time now, he is elected fellow of the National Academy of Sciences, NASI, in 2023. He received Indian National Science Academy Gold Medal for Young Scientists at 2000. I think he doesn't need any introduction, but this was just a brief introduction. Professor Arvind, please.
No. When I said 5 minutes, the organizers said 3 minutes. See, the point is, what I'm going to do in these 3 minutes is more important. See, interdisciplinarity in science, or for that matter, in any domain of knowledge, is extremely important. And this year's Physics Nobel Prize is an example of that, because there was a lot of controversy and criticism. Also, some people were saying, why has Hupfield been given the prize in physics and all that? So that I will leave to the speaker in case you have questions. But let me tell you how interdisciplinary thinking can help us. There is a concept of contextuality in quantum mechanics, which roughly speaking is the following, that if you have a quantum system and you make a measurement of an observable, you all know that you get one of the eigenvalues of that observable, and after that the wave function collapses. Now, if you have two commuting observables, then they can be measured together simultaneously, and if you have non-commuting observables, they cannot be measured together. They don't have common eigenvalues. However, the following peculiar situation can arise, that observable A commutes with B so that they can be measured together. A also commutes with C so that they can be measured together. But B and C do not commute. Which means, now what value, how do you interpret values of A? So what we say is that you have to specify the context as to which other observables you are measuring along with A. And A reveals different values in different companies. You see, this is the quantum contextuality, which is a very hot topic of research today because of quantum information, quantum computation, all that and so on. While explaining this concept, I mean, in the classical world, this does not happen. If you have a phase space point, all observables can be derived from that phase space point PQ for that particle, or for that matter, even if you have n particles. However, in life, this is very much true. If I know a friend in my friend circle, you know the personality of that person to a very good extent. Then you go to his home, and he has brothers, sisters, family. there the personality is going to be very different. So, and the family may not even know how a person is behaving with friends. So, which means as humans also, we reveal different aspects of our personality based on which context it is being revealed in. So, contextuality is very much there in life. And now it becomes easier to understand quantum contextuality. Whereas if the vintage point is always classical physics, then quantum mechanics looks very bizarre. However, if the vintage point is broader, particularly behavior, human behavior, and so on, then quantum mechanics looks intuitively simpler. Another example, which is very intriguing, which I recently read about, which I will share with you, and then I will stop. People are talking about a new subject is emerging called quantum cognition. Now, this quantum cognition is not about neurons following quantum mechanics. No, that is something which we don't know, and people have talked about that, and there are a lot of discussion. It is at a very broad level how quantum-like ideas might be there in our thinking. As I told you, contextuality. You see, the following experiment was done that there are people who are criminals, and punishment has to be decided, and the data is given to a group of people, whether they should be executed or not, and statistics is collected. Then, before you take your decision, you are just, with the same data, you first have to make up your mind whether the person is good or bad. So one is a single measurement process, one is two measurement process, which we call sequential measurements in quantum mechanics. And to the surprise of the people who did the experiment, the results are different. If you force a person to first select a subset of the answers and then choose one from that subset, human minds work differently if you directly ask that question. So this is again very much like sequential measurements in quantum mechanics. So all I wanted to say was that interdisciplinarity should not be underestimated. This year's Nobel Prize, in some sense, is in a very, very upcoming, interesting area. And the area has been around. Lots of people think artificial intelligence and neural networks is a new area. This area, I mean, these ideas have been there from 1960s. This is not at all new. Only that now it is being used in a very big way. So with these words, now let me also say those pleasantries which one is supposed to say from this dais when you come in this role, that it's an extremely, extremely important initiative being taken here in the series of lectures. And I think this should go a long way. Of course, it would be much nicer if many more students join these lectures, and we should be able to attract many of them. Specifically, I would like to say that in the past 1 decade, Professor Grover has put in so much energy into broadening the horizons of science and knowledge in Chandigarh, Tri-City region, Northwest India. So I think in the next 10 years, maybe we will see some very important outcomes of it, of these efforts, because it takes time to nurture science and then have scientists move forward with those ideas. Takes time. So I would specifically say that amount of time and energy he has put in personally, it's really remarkable. SPSTI, I should not say anything. I'm one of the founder members, so it's my own organizations. When this organization was being conceived, all the meetings we had were in IISER and so on. So it's an organization which is really done what it started to do, and is growing. The initiatives and activities are growing. And that's again very remarkable. So let me not come between today's lecture and you, and let's know what has happened. What is the research behind the Nobel Prize given to Arvind in this year? Thank you.
Thank you, Professor Arvind. And I hope you will expand those first 3 minutes into 30 minutes and then many more minutes. And we have an opportunity to listen to you in this year of quantum technologies, quantum sciences and technologies. Thank you. I will now request Professor Vipin Bhatnagar to introduce Professor Vipin Srivastava. So Vipin to Vipin.
Thank you, ma'am. So good afternoon, everyone. So I can start by just saying like that, not just a physicist. That's we can summarize our speaker today. It is my privilege, and I'm very happy to have this chance to introduce to you our distinguished speaker today, Professor Srivastava. We share the first name. Former Vice Chancellor and Dean at University of Hyderabad, and a senior faculty member at the School of Physics. So he would be talking to us today in a series of lectures and on 2024 Nobel Prize in Physics. I'm sure, as our guest of honor, Professor Arvind, mentioned, that there was an element of surprise when those were announced. So many people from the main physics domain were taken back when the announcement was done by the Nobel Committee. So Professor Srivastava is a trained condensed matter physicist and has but always been engaged in many interdisciplinary, main disciplinary research areas. And it is worth noting that he has been working in neuroscience for more than 25 years in collaboration with University of Cambridge. And though he's a trained condensed matter physicist, theoretical physicist, and he also was the central force in setting up the university's Center for Neural and Cognitive Sciences and during 2006 and 7 at University of Hyderabad. So we will hear from him about the story behind the Nobel Prize in the first lecture, the hidden physics and neuropsychology in the 2024 Physics Nobel Prize, a revelation. So we may get to learn how the committee decided to give this prize to something which is not completely coming from at the face value, like from the physics, the main domain. And the second lecture will be followed by what do we have beyond Hopfield. So Hopfield and Hinton, they were given the prize. And so what is there beyond Hopfield? So let's welcome Professor Srivastava, and let's learn about the stories behind these 2024 Physics Nobel Prize. And I again welcome you on behalf of the Physics Department. Thank you.
इंटरफेयर तो नहीं करेंगे so yeah. So very good afternoon. I feel quite privileged to speak to an audience which has several very distinguished senior persons. That makes me a little bit conscious. But I am very grateful to my old friends, Dharamveer and Kia, and Professor Grover, to give me this opportunity to speak to you about 2024 Physics Nobel Prize, which has drawn attention of a large cross-section of people, because the underlying theme of it, the neural networks, is almost a household term these days. People from so many disciplines are working on neural networks and using it as a tool. So although it attracted attention of such a wide spectrum of people,
But most people were lost as to why this prize was given to physics. Where is the physics in it? And some of my friends asked me, who were computer scientists and also some physicists. So I realized that even a lot of physicists are not aware as to what is the physics in the neural networks. Okay, so that's why I have given the title the hidden physics and neuropsychology. It's not only physics that is hidden in the neural network, but a very important component of it is the neuropsychology. So all this should be explained. So I'll try to explain it in very simple terms, because I gather that it's a very mixed audience. So so indeed, when some people ask me where is the physics in it, I looked at the citation, and all it says is tools they have used. Hoffield and Hinton have used tools from physics to learn machine learning and associative learning, associative memory and things, pattern recognition. And I even scanned through the detailed citation, and nowhere I found any indication of spin glass theory, which is at the heart of it, being mentioned even obliquely. I was quite surprised, and I found it a little unfair. That I'll tell you why I felt bad about it. So now, in order to understand, as I said, that there are two hidden factors here, we have to go back in time and see what are those hidden components. And so this actually reminded me of a good quote from Steve Jobs, that you can't connect dots looking forward. You have to look backward to connect the dots, right? So two major dots that exist in this context are the theory of synaptic plasticity that comes first, historically, and then the theory of spin glasses in physics. So these are the two premises on which the neural network idea rests. So now we need to understand, the central thing that we need to understand is that how does physics help a machine, in this case a computer, learn and memorize? After all, we all know that computer computes. So this raises a question of the meaning of computability. What is computable, and how how physics comes into it? So again, we have to go back to back in time in order to connect some more dots. And so if we start from, let's say, 1926, we realize that, first of all, Hilbert talked about the computability of mathematical functions. And he said that if you can write an algorithm for a mathematical function, then you can compute it. But it turned out that it was not as simple as that. Later on, it became a full-fledged field of research, namely computability. And these three famous names, Gödel, who is known for his incompleteness theorem, a mathematician, and Alan Turing and Church, they did a lot of work, and they invented a hypothetical machine called Turing machine, right? It's a hypothetical machine, and that actually defined computability. Whatever could be computed using the Turing machine was defined as computable. And if that was not possible, then one said that. So there is it's a huge subject now. And as the technology progressed and electronics improved, von Neumann built the first computer. And so whatever this computer, the electronic computer invented by von Neumann could do, that was termed as machine intelligence. Okay. So, but while all this was going on, the curiosity was always there to decipher as to how the brain computes. We are trying to make computers and so on. But then the effort was always to derive inspiration from the brain as to how it computes. Okay? So that's where the term artificial intelligence emerged. That is, making a computer learn, memorize, and recall the way computer does was termed as artificial intelligence. Okay? So this was the story like up to 1940. And the first couple of people, a set of people who used the ideas from the brain, namely neurons, were McLaughlin and Pitts in 1943. They first used the physiology of neuron to see how the neuron could compute. Okay? But this was very, very rudimentary. And not much progress was made. So historically, major breakthrough came only in 1949, when Donald Hebb, a Canadian neuropsychologist, discovered what is now an established term called synaptic plasticity. Okay? I'll just explain what is Hebb's the synaptic plasticity, what it means. And so as just a very quick rundown on how the brain is built, it comprises about 100 billion neurons, and they are very highly connected. And the connections are called synapses. So there are on the order of 10 to the 15 synapses. Okay? So each neuron is connected to thousands of other neurons, and they are all connected through. So this is a sketch of how the two neurons are connected. So as you know, there is a lot of electrical activity that goes on in the brain all the time, right? So the neurons fire, they exchange what is called action potential. These electrical impulses are exchanged between the neurons. And so if this is the presynaptic neuron, this is the axon, and here is the synapse. So synapse is something like this. This end of the axon has a synaptic bouton, and then there is a small gap, and this is the next neuron, the postsynaptic neuron. Okay, this is presynaptic, and there's the postsynaptic neuron. So the neuron has axon, and then lots of branches here. They're called dendrites. Okay, so the axon, the end of the axon touches one of the dendrites, one of the branches of the dendrites. Okay. So when this neuron fires, it sends the electrical impulse or the action potential. And then when it reaches there, it triggers some neurotransmitters to be released. Okay. It's a beautiful mechanism which is given in any textbook on neuroscience, I believe. And then these neurotransmitters go to the next or the postsynaptic neuron, and they can either excite the next neuron to fire, or they can inhibit it, discourage it from firing. Okay, so this kind of signal is received to each neuron from thousands of other neurons. Some of them try to excite it, others try to inhibit its excitation. So the potential on this postsynaptic neuron increases. Can I get some water, please? It's for the bottle. So the potential on the postsynaptic neuron goes up or down, okay, depending on the signal it receives is excitatory or inhibitory. But in the end, everything adds up, and if the potential here exceeds a threshold which is built into the neuron, if it crosses that threshold, then this neuron fires. Otherwise, it remains quiet. The neuron can either fire or remain quiet. Okay. So what Donald had found out was that if a presynaptic neuron excites the postsynaptic neuron constantly, repeatedly, then the synaptic connection between them, or what is called synaptic efficacy, it changes in an irreversible manner. That is, the change happens plastically. Okay, that's why it is synaptic plasticity. So what was realized was that when we are learning, when we get an information, the neurons start firing. Some neurons fire, some do not fire. Okay, and in the process, the synaptic efficacy of all the neurons changes, and it changes irreversibly or plastically, right? So this irreversible or plastic change in the synaptic lies at the heart of the mechanism of learning, right? So this is the physiological mechanism of learning. Right. So this happened in 1949. Again, this gave impetus to a lot of activity in neuroscience. However, insofar as the understanding the computability or the computing capacity or computing capability of the brain is concerned, it didn't take us too far until 1982, when John Hoffield adapted the ideas from spin glass to understanding the computability of the brain. Water again. Yeah. Right. So this happened in 1982, although the spin glass theory was given in 1975. Edwards and Anderson gave. Thank you so much. So I'll give a quick rundown on spin glass, okay, and then explain as to how Hoffield connected spin glass with synaptic plasticity and gave the idea of neural network. So spin glasses are alloys. For those who are not from physics, would know that in any material, the atoms are arranged in a lattice. So in this case, the lattice primarily comprises non-magnetic elements like gold, copper, silver. But in them, a very small concentration, much less than 10%, of some magnetic elements like iron, manganese, and chromium is mixed. So this is a random alloy in which these magnetic elements are distributed mostly at far off distances, right? So the magnetic atoms have net magnetic moment, which is represented by an arrow or spin, as we call in physics. Okay. So there are these magnetic atoms distributed all over the system at various distances, mostly long distances, and they interact with each other. And this system has many, many interesting physics-related properties, which is not our concern here. But one of the most important or peculiar property of spin glass, which concerns us here, I will explain in the next slide. But the physics, the interesting physics of spin glass was done by Sam Edwards and Phil Anderson. Anderson, you remember there was a long meeting, 3-day meeting very recently, same Anderson. And they gave the first theory of spin glass way back in 1975. And just very little later, Sherrington and Kirkpatrick gave a simplified solvable model for a spin glass. So we are not going to go into the details of the spin glass theory, but the aspect that interests us here is the peculiar long-range interaction that exists between the magnetic atoms. Okay, and that interaction has this character. So Jij is the interaction between two spins I and J at position I and at position J. And the most peculiar aspect of this interaction is that it changes from being ferromagnetic to antiferromagnetic. Okay, for the convenience of those who are not from physics, a ferromagnetic substances, in the ferromagnetic substances, the spins are aligned parallel to each other like this or this. And in antiferromagnetic, they're aligned anti-parallel to it. Like, up and down and down and up. Okay. And interestingly, this depends on the separation between the two interacting spins. If the separation is in this range, then the interaction is ferromagnetic. If the separation is more, like in this range, then it is antiferromagnetic. Again, ferromagnetic, antiferromagnetic, and so on. So this is a very peculiar kind of interaction that happens between the spins over long ranges. Okay, and that is key to the analogy that John Hopfield utilized, and I'll tell you how he did it. But first, because of this peculiar nature of the interaction, there is a very interesting phenomenon which is called frustration. And what that means is that let us just, for simplicity, take the example of 3 spins. Okay? So suppose the interaction between these two is that they are ferromagnetic, so they are oriented parallel to each other. And suppose that this spin wants this particular spin to face up, but this wants it to face down. So this spin will be frustrated now. It wouldn't know whether it should face up or face down. Okay? So like this, all 3 spins you can see can be frustrated, are frustrated. So this means that there are 2 raised to the 3. We are now considering a simplified picture of only spin up and spin down, which is called Ising model. Okay, so this is again a simplification to the theory. Okay, so in the Ising situation, there will be 2 raised to the 3, that is 8 possible configurations of up and down spins in a triangle. Okay, so now you imagine if there are n spins, a large number of spins, and they're all interacting with each other, and the interaction is of this kind, which creates frustration among them. So there can be 2 raised to the n possible configurations that will be allowed. Okay, and in quantum mechanics, that is allowed. So there are so many configurations of spin up and down, which minimize the total energy of the system. So in physics, total energy is very sacred, and it has to be minimized for the state to be stable. Okay. Now, so we talked about this interaction Jij. So I like to call it a discomfort function, because discomfort should be minimized, or Hamiltonian in physics, which is very sacred. So the Hamiltonian for spin glass is written like this: xi I and xi j are the spins on I and j positions, and jij is the interaction between them. Okay, and then you sum over all the spins. Okay. So Hoffield took the analogy like this, that the neurons are firing or not firing. So that is like spin up or spin down. Firing, not, or quiescent, or up or down, or we have to designate them by numbers because we have to do computation. So +1 and -1. -1 means quiescent, 1 means firing. Okay. And then they interact with Jij, and I will explain the form of the Jij, the mathematical form, in the next slide. So basically, as I said, when an information comes to the brain, it triggers a lot of firing and not firing activity, and and everything settles down with a pattern of up and down spins, okay, or a set of plus or minus ones. Okay, so every information is now represented by a vector whose components are plus or minus 1, like this. So an object or an information, whatever it may be, that comes to the brain and triggers the neural activity, is now converted into a pattern of plus and minus 1, which is like the pattern of spins in the previous slide, right? This is a simplified a triangular example of up and down configuration of up and down spins. Okay. So this is the analogy. This is how he took the analogy. But we need an expression for the Jij to suit the Hebbian hypothesis of plasticity, right? So incidentally, that was also done by a very well-known physicist, Leon Cooper, of superconductivity fame, Bardeen, Cooper, and Schrieffer. That same Cooper, he wrote down this expression to represent the Hebbian hypothesis or Hebbian plasticity. Okay, the Hebb's plasticity. So now the stage is set. We have lots of spins which are to be identified with neurons, firing and not firing neurons, and they are all interacting through an expression like this. You just keep an eye on this expression. Xi I, Xi j are the two neurons, I and j, and mu represents a particular configuration. I'll come to that. So now let us take this simple example of 5 neurons and see how the patterns are learned and how they go into the memory. Okay, so suppose we start with a situation in which the synapses are zero, right? They have not been changed. We call it tabula rasa, although it is, again, it is not realistic, because when a child is born, the child is born with a lot of information. And here we are saying that for simplicity, let us assume that this network of 5 neurons has no information to start with. Okay? And the first information comes to be recorded, in which this is up, this is down, up, down, down, like this. One random pattern is coming to be stored. So between these two neurons, the synapse will get modified following this rule, which is a mathematical manifestation of Hepp's hypothesis or Hepp's rule. So these two will be multiplied and this will be -1. So this synapse will be modified and its value will be -1. This synapse will be modified and its value will be +1. Mind you, biologically, those who are very particular about biology, there are serious biological flaws in this expression, right? So I'll come to that much later as to why those flaws were ignored. Okay. So like this, this pattern of up and down spins has modified the synapses like this, and these synapses are modified with these values. Their efficacies are now -1, -1, +1, and so on. So this is how the first pattern is stored or saved in the synapses, in the network of synapses. Now suppose second pattern comes to be recorded. And this is the pattern -1, +1, +1, -1, -1. Okay. Again, these synapses will be modified following this rule. Okay. And so this becomes -1, this synapse becomes +1, and so on. Now this change will be added to the change that has happened earlier. So this -1 will add to -1, and this synapse now will, after the second pattern, will become -2. 2, -2, 2, 0, 0. So now the synapses, after the two patterns have been learned by the system, have been modified like this. Okay? And this we claim that now this network of 5 neurons has stored one pattern and second pattern. Okay? And they have been stored in the form of these changes in the synaptic plasticity. Okay? So now you imagine that the third pattern comes, fourth, fifth, and so on. And they are all stored in the form of changes in the synaptic plasticity. So all these are added up. See, sum over mu equal to 1 to p. So mu is pattern 1, pattern 2, mu equal to 1 and mu equal to 2. Like this, suppose you have gone through p, some large number of patterns. Okay? So they will all be stored in the form of changes in the synaptic plasticity. And you can imagine that after, let's say, 50 patterns or 60 patterns have been stored, these synapses would have changed like crazy, right? So now, all this, we can claim that these patterns have been learned and memorized by the system, or memorized if we can retrieve them. If we can recall one of the patterns from this jumble, then only we can claim that yes, this pattern was not only learned, but actually it was memorized. Okay? So for retrieval, the prescription that was adopted was again the same thing. It is associative, because now a new pattern, now one of the patterns will be presented to the network again, and it will be checked whether it can be retrieved or not. It can be recalled or not. Okay, from this jumble of changes, highly modified matrix of JIJs. Okay, so seems like an impossible thing that, if you have stored so many patterns, how is it that one particular pattern can be recalled or so if it can, so it is done associatively. Memory, there are so many different types of memories, but then in neural network jargon, we only talk about associative memory, okay, in which we present a pattern. Suppose we have learned about this bottle, and I present it after so many patterns have been learned, and check whether I can retrieve this particular pattern corresponding to this particular bottle or not. Okay, so when this is presented, it will again trigger the firing and not firing activity the way it did in the first instance. Okay, but now all the synapses which have been changed drastically will be involved in when the what you call the action potentials are exchanged. So now the action potential, like this fires, and then this will send the action potential, but now it will go to this through this synapse, which is highly modified. Okay, so like this. So suppose we have 9 neurons, and we concentrate on 9th neuron. So a field will be created on 9th neuron by all the rest of the neurons. So again, it's a simplified situation in which each neuron is interacting with every other neuron. That has been introduced only for simplicity. I mean, each neuron can interact with thousands of neurons, but not all the other neurons. Okay, so here for simplicity we take so let's say we have 9 neurons and we have highly modified JIJs. Then there will be a field created on this represented by H. So like this, all of them are exchanging signals. So the fields on all of them will be changed, will be created. They are called local fields. Okay, so now this local field is to be compared with the activity that it originally created when it was presented for association. Okay, so this is the prescription. Mathematically, this is the prescription we apply. If this product is positive, then we say that the spin that it created agrees with the original spin. Okay, and if not, then it's bad retrieval. So when this bottle, when it was presented for association, the pattern it creates, and then the pattern that gets modified because of the modified JIJs, if the original pattern and the modified pattern, they agree with each other, then we say that it has been retrieved. It's a very simple exercise to do on computer, very, very simple thing, very simple program does this. Okay, so if the retrieval is successful, then we say that we have the associative memory, right? So this is the story that when we are learning, when we are making the system learn, all these JIJs or the synapses get modified, and the information about each pattern is stored like stacked on one on top of the other. And from this stack, we have to pull out one particular memory. Okay, and interestingly, that happens, right? So that's why it became so popular that it does the job. So here is a simple simulation with 1,000 neurons. Okay, and So when you do this, you get something very interesting. In fact, not interesting. Something which is very disturbing. So initially, they are all, whatever patterns you provide, they are learned, and when you try to retrieve, they're all retrieved. But then there is a limit to it, and that limit is defined here, that if the number of patterns stored exceeds a certain number, then the whole system collapses. And that's an embarrassing aspect of this Hoffield network, which I'll come to at the end. And that will be, my next talk will start from there. Okay. Right now, let us postpone talking about that bad aspect called memory catastrophe. But right now, you see that even though the JIJs have been modified drastically in the course of learning one pattern after the other, but to a good extent, you can retrieve whatever you have fed in. Okay? So this is the result. There is another very interesting aspect, which is interesting from the cognitive point of view, and that is that, as I said, you have learned about this bottle earlier, along with so many other objects, and then you present it, and you can retrieve this information about this bottle. But what is also possible is that you can give a distorted or partial version of this bottle, and that will still be retrieved. This bottle will, the pattern corresponding to this bottle will still be retrieved. Like suppose you just show a part of this, and when you present that, even that can be retrieved. Okay, and that is there in the. How am I doing with time? Okay, so I'll just quickly finish this, and then ask questions. Yeah. So this is called. This was the associated memory, and it has an interesting property. So all these patterns which were memorized, they are represented by valleys in this landscape. So this is an energy landscape in which the XY plane has, this is, we have drawn it in 3 dimensions, but this is actually an n+1 dimensional space in which the XY plane has all the 2 raised to the n possible configurations of the patterns, 2 to the n patterns, and z-axis represents the energy. Okay, and these valleys represent the patterns which have been learned by the network. Okay, and then this is called basin of attraction. This thing. So there are a whole lot of other patterns which are different from the one at the bottom, but similar. Right? So those patterns, those other patterns or configurations of spins represent objects or information similar to this one which we are interested in. Okay? So when we present that, let's say a pattern here, and subject it to the retrieval process, it will slide down and converge to here. That means it will. So this is like, we all recognize our house, and no matter from which angle we look at our house, from what distance, what part of the house, we can still remember, we can still recognize that it is our house. Okay, so something like that. Okay, so this is, skip this. So as I said, there is a memory blackout, memory catastrophe. And that is that if suppose you have 100 neurons, network of 100 neurons, you can go only up to 14 or 15 patterns. You can learn 1 to 14 patterns sequentially. But if you stuff it with more patterns, even 2 or 3 more patterns, then everything gets spoiled. Nothing is retrieved. That is called memory catastrophe or memory blackout. This was a very embarrassing flaw in Hoffield's network. Okay, and in the next talk I'll explain why this happened. But insofar as this talk is concerned, I think I will summarize it like this: that Hoffield combined the results from results of synaptic plasticity from neuropsychology with the ideas from spin glass and built a model for cognitive learning and memory. Okay, so his idea first of all was to understand how the brain learns and memorizes. So he gave a very crude, so this is a very crude toy model, right? But good enough to fetch a Nobel Prize for cognitive learning and memory. And so this is how he built the artificial neural network. And so I would say that 2024 Physics Nobel Prize was awarded for an invention, not for a fundamental discovery. Most of the times, so I think the Nobel Committee deviated in this case, and earlier also it has done it. And I think this year's chemistry prize also was like that. So I would like to, in the end, I would like to say that the Hoffield's work progressed in 2 directions. Predominantly, the idea of ANN, artificial neural network, was exploited by computer scientists to make tools tools for machine learning and pattern recognition. And in that direction, enormous amount of work has been done. But there is another direction in which some research has happened. Very few people, and we are among those minority groups in which we try to improve the biological shortcomings in the Hoffield network and try to make it more cognitively appealing. Okay, so this will be the subject of my next talk, which will be
Say plasticity is reversible. If you take
yeah, well, here it is used in that sense that plastic means you have reversed it, whereas elastic is you leave it and it comes back. But yeah, I mean, strictly speaking, any plastic material can be also reversed, yes. But here the idea is plastic means that once the synaptic efficacy has changed in the process of learning, it stays there. Again, it stays not forever. It can also change. There are subtle neuroscience aspects to it. Yeah, right. So because the neuron is treated was treated by Hoffield as a binary object. That is, it either fires or it doesn't, which is true, right? So neuron receives impulses from all the other neurons, and the potential can go up or down depending on the nature of the input. But the net, after everything is added up, if it exceeds the threshold, then it fires. And sometimes when it doesn't exceed, then it remains quiescent.
Biological system, doesn't happen.
The memory catastrophe. Yeah, no, that's the idea that, see, although the catastrophe defines the memory capacity as 14%. That is, if the number of neurons is n, then 0.14 n will be the capacity. Okay. Now, n in reality is about 100 billion, and 14% of 100 billion is a huge number. And I'm sure that is good enough to store whatever we learn in our lifetime. But the idea which is not appealing here is that what this means is that if the brain is overloaded, then it gives up. It gives in, that it fails. That is not correct. I mean, we can, yeah.
Often say one day before the Nobel lecture on 9th of December, he says, my short memory has fainted.
Yeah.
But my present memory,
I'll mention about this in my next talk. Yeah, the short term and the long term memory. That's a wonderful question. Yeah.
that my short term memory has totally gone.
Yeah, I know.
Long term is still alive.
Yeah. That happens with most of us.
The neuron is based on pumps, hydrogen pumps also.
Okay.
The movement of the sodium potential, change of sodium and potassium.
Yeah.
But the artificial, this lean machine, this system is not working. But
Yeah, those details are not really taken into account.
That's what I keep thinking.
Yeah.
That is sodium potassium pump. It fire an impulse, it goes through the neuron, then touches the synapse, sodium goes out, potassium comes inside. That mechanism doesn't work in the computer.
Yeah.
Inspiration is that. Like if we change the by Pauli exclusion principle, the spin, both anti-clockwise or clockwise, we can change the mechanism. We'll discuss it in the
Yeah. But from the biology point of view, the Hoffield model is very crude. As I said, it's a very crude toy model. It hardly takes any biology.
That it's biology based. There is hardly any biology.
Yeah. I mean, he only takes the idea that the neuron can fire and not fire. So it's a binary entity, right? Yeah.
As I take Sanskrit in class 4th or 5th, I use Sanskrit in my biology class. I'm inspired by that, not that it's some other thing.
Yeah.
That's what, why we Cambridge 2 months back, we discussed that. And we'll discuss.
Yeah, but I'm good. I'm glad that you mentioned long-term and short-term memories. So that is something which I'll in the next talk I'll.
He said it in my short memory.
Yeah. So the mechanism of long-term memory and short-term memory are different, and yeah. So we have made a proposal in that direction also. Just a proposal. Yeah. Thank you. Yeah. काम कर रहा था ना